So now with what we're moving on to in 1.2, we're talking about geometric sequences in series. And these types of sequences might look something like this: 1, 2, 4, 8, 16, and so on. Well, I don't have a common difference, right? I'm not adding the same thing to get from term to term. I'm multiplying the same thing to get from term to term. In this case, I'm multiplying by 2 every time. So this common factor, or I guess this common ratio, we're going to call it, right? We're dealing with the ratio between terms. This common ratio is what helps us generate the terms of the geometric sequence. And we're going to call it R for ratio. So just like we did with arithmetic sequences in series, the next thing we want to do is try to find some general rule that's going to let us generate the terms of our sequences, but also express any geometric sequence using this term. So let's just take any old sequence, and if we want to talk in general, we'll call it u sub 1, just like we did with arithmetic sequences. And to get to the next term, u2, I'm going to take u1 and multiply by r, just like I did up here, right? I took my first term and multiplied by the common ratio. And I can do this for the third term, right? Take the previous term, multiply by r, right? To get to 4, I took 2 and multiplied by 2 to get to 4. Well, we can also think about this in terms of the first term, right? I started at the first term and I multiplied, well, we can kind of see here, I've multiplied by r twice, so that'd be times r squared. And we see that with our kind of concrete example. I start at 1 and I multiply twice. And to get to my fourth term, same idea. I can either multiply the previous term by r, or I can start at my first term and multiply by r 3 times. So if we want to speak in general then, my nth term, term number whatever I want, I can take my first term and multiply by r how many times? Well, if you've noticed, again, to get to my second term, I've multiplied by r once, third term twice, fourth term 3 times, n terms n minus 1 times, always one fewer r than the term number I'm on. And sure enough, this is going to be my general term of a geometric sequence. I'm just going to call it GS for now. So to summarize that, a geometric sequence with first term u1 and common ratio r has a general term un. Actually, I'm going to move this lower, I think. Has general term u sub n, u sub 1, r to the n minus 1. This is our general term. So for example, find the common ratio and write the next two terms of the sequence. So let's look from term to term. I just want to know, what do I have to do from 2 to 2.5 to get to 5? And also to 5 to get to 10. And I obviously can't add the same thing, but I can multiply the same thing. I'm doubling each time. So I'm multiplying by 2. So my common ratio is 2. And the next two terms, well, I'm going to double it again and double it again, 20 and 40. If I did want to write the general term, I could, right? U sub 1 r to the n minus 1. Right? 2.5 times 2 to the n minus 1. And it's worth noting here that I can't combine these. Please be careful of your order of operations. I cannot take this expression and I cannot combine the two numbers. It does not work that way. Don't ever do this. Please don't ever do this. It's never true in general. So these are their own things. Again, we can almost think about having like imaginary parentheses here, if that helps you. Let's stick with something else. Let's try something else here. Find the number of terms in the finite geometric sequence given here. Well, I suppose we could count, but we don't know if this is a relatively close term, right? This could be the 5th term, but it could also be the 105th term, and I don't want to waste my time dividing or multiplying by the common ratio in order to count and hope I don't lose count. So let's find an easier method. if we want to find the number of terms in past problems that we've done this with arithmetic sequences, I'm clearly having a hard time saying that, we want to know n. The number of terms is n, right? That's what it's always meant. So I want to find n terms, and I can figure out a couple things from this. I know my first term is 440, and I know my common ratio is what it looks like to get from term to term. Pick a different color here. To get from term to term, I'm either dividing by 4, or we're better off looking at this as multiplication every time. So let's actually express it as multiplying by 1/4. And it seems just from our first two examples that that seems to be our common ratio. So our common ratio is 1/4. And we also know that our last term, whatever term number it is, term number n, is 0.4296875. And our goal is to figure out what number n is, right? What term number is it? So that's our goal. So let's play around with this a little bit. We know that u sub n, whatever the nth term is, we can express that using our formula, u sub 1 times r to the n minus 1. Well, this time we also know that u sub n is equal to that number right there, 0.4296785, sorry. And we know that u sub 1 is 440, and we know that r is 1/4. So what I'm doing here, 6875. What I'm doing here is saying, well, I think a lot of times when we're dealing with sequences, it helps to find the general term if you can, always, as just for if for no other reason than just to give me something to kind of ground my work. We may not always use it explicitly, but I think it can be helpful oftentimes. Just to know what that general term is in case I need to play with that term specifically, or if I need to just generate any other term. So I'm finding my general term here so that I actually kind of know what the sequence is. And I want to know, when does this sequence equal this number? And to do that, at this point, because we haven't learned how to solve exponential functions, exponential equations, we're going to need to turn to our calculator. And I'll show you in just a second what that'll look like. But all I'm going to do, I now have an expression for my function, right? I now have a way to express my sequence, for my sequence. I have a way to express my sequence in general with a variable. And I want to know, well, what value of n, say what n, makes that expression equal to the number that I'm given, equal to 0.4296875. So let's actually use our calculator to do this, because we don't know yet how to solve these kinds of functions otherwise. So the first thing I want to do is treat this like a function. So I'm going to go ahead and enter in that general term as if it were a function, as if I were going to actually graph this function. And I'm not going to here, because we're trying to do this in reverse, right? So we're not going to press graph, but we are going to use this table function. So if I press second table, it generates a table of x values. So in this case, our x values are actually n, right? Because we're just making the switch so I can use it on my calculator. So in this case, x is my term number, and y gives me the actual value of the term. And I want to know, at what term do I actually get 0.4296875 that I'm looking for? Well, if I look through my table, I don't see it explicitly, and that's just because of the way that our calculator is going to round. So I'm going to look for something close enough for now, and I see that this seems to start pretty darn close to the term value that I'm looking for. So let's explore this a little bit more. Let's head down here, and then you can see that your calculator gives you a more exact answer. So 0.4296875, it seems to appear in term number 6 of the sequence. And now we've just got the answer. It's just It's just right there. That's all it is. So I want to explore one more type of problem in this part of the video. And it's one that's similar to one that we've seen with arithmetic sequences, right? The fourth term of a geometric sequence is 54, and the sixth term is 486. Determine the possible values of the common ratio. Let's approach this the exact same way that we did before. Right? We don't know much information. In fact, we don't even know exactly how to solve this problem yet. But we do have some given information that we can play with. We know that the fourth term is 54, and we can express that, right? U sub 4 is 54, but we also know that we can express U4 by saying it's the first term times the common ratio cubed, 3 to the third power. In other words, we can kind of condense this and just say that U1R cubed is equal to 54. And we also know that the sixth term is 486. So again, U6 equals 46. I could also express that using my formula. And again, I could just skip right to equating these. Let's also keep track of our goal. Our goal is to determine the possible values of the common ratio. This is our end game. This is what we're trying to do. Well, I've got two equations here. I know that U1R cubed is 54. And I want U1R fifth to be equal to 486. I've got these two what we call simultaneous equations, and we want them to be equal. Or sorry, we want the same values for U1 and R to satisfy both of these. That's what I'm trying to say. All I want to do is find the value of the common ratio, so I don't need U sub 1 at all. Let's make a substitution. We can't really solve these by elimination, as obviously. In this case, elimination actually is the better way to go. So I want to get rid of U1. U1 is just going to be 54 over R cubed. And I'm going to go ahead and plug that in here. So 54 over R cubed times R to the fifth is 486. And I can simplify this again. I can say 54 R squared, right, using my laws of exponents, equal to 486. Divide by 54. I've already done it, so I know R squared is 9, which means R is either plus or minus 3. There's no condition on R that says it has to be positive, so both of these solutions are valid. These are also both valid. I didn't want to do that because we don't know any other information. We don't know if between the fourth and sixth terms, if the fifth term is negative or positive, right? That would actually tell us whether or not we need to pick a positive or negative R, but we just don't know here. So the possible values of the common ratio are 3 or it's negative 3. And if I wanted to, I could actually go through and finish out the system and express the two common ratios if I asked for it. I didn't here, but it's good practice for now. So let's actually find U1. U1 is going to be 54 over either plus or minus 3 cubed. Well, if it's plus 3 cubed, then it's 54 over 27, which is 2. And if it's negative 3 cubed, it's 54 over negative 27, and U1 is negative 2. So I guess we wind up with two sequences, I suppose, right? We end up with 2 times 3 to the n minus 1, or we end up with negative 2 times negative 3 to the n minus 1. Either of those sequences could be valid. Both of those are valid answers. We just don't know which, but both of those would be acceptable geometric sequences for the information that I was given. And that's okay. It's okay to conclude that there are multiple possible answers. We can have these kinds of discrepancies as long as we acknowledge that it's due to the fact that we don't have the information that we need to be any more specific.